Another use of a dimension analysis is that we actually can form a formula equation using the experimental result. And this kind of equation is what we call the empirical equation, which is based on an experimental observation. So we can construct it using the dimension analysis. Now I think we better directly go to the example. Here we have mass m is attached to the spring, and the spring obey the Hooke's law, which given by the force equals to kx. So F equals to minus kx, and this F is a force, and this k is a spring constant, and the x is the displacement, right? And this thing actually we will talk more and more detail in a later video. So for now, let's consider this experiment. Observe that the period of this oscillation t, this t is a period of the oscillation. It depends on the spring constant. That means you use the different string which have a different spring constant, and you hand on something of a different mass on the spring, you get the different period of oscillation, different t. So now we are asked to construct the empirical equation for this period t. Actually, what we are doing is we are relating the period t to the k and the m, to the spring constant and the mass. Now the question is how, and how we can use the dimension analysis to do this. Let's draw a diagram so you can see how this experiment is carried out. First thing, we have a wall, and we have this frictionless surface. Now we have a mass here m, and we attach it to the spring. This spring have a spring constant of a k, let's say, and here is a equilibrium point. We pull this mass some distance x from the equilibrium point. So let's say here this is x distance away from the equilibrium point, and we let go of this mass, so we can clearly see this mass will oscillate back and forward here. If this mass start with this point here, let's say point A, and it end with the point A for one complete oscillation, the time taken is what we define by this period, which this is a period t. This is a definition of a period. Now, from the experiment observation, we observe this period t, capital T, is depend on the spring constant k and the mass. That means if we change the spring with a different k, or we change the mass, it gives us the different result for this period t. So let's construct this empirical equation for the period t using the dimension analysis. So what we can write is that the t is proportional to the k power of some alpha and m power to some beta. Now here is the proportional. We can write this t is equals to ck power to the alpha and m power to the beta. This c is what we call the proportionality constant. In terms of a dimension, we know the dimension of this period is a t. Now let's find out the dimension of this k. From this formula, f is equals to minus kx. We get k is equals to f over x, and we know the f is equals to ma, which have a unit of a kg meter per second square. In terms of dimension, this is m l length, dimension of length, and t the dimension of time power of a negative 2. And you can see this is dy by x, and this x have a dimension of the l. You can see this will just cancel out, so the dimension of this k is just the mt power of a negative 2. Now you see this equation here, this k have a power of alpha, right? The whole thing we copy back the dimension m t negative 2 whole thing power of alpha, and now this mass have a dimension of the m to the power of a beta, right? So this is equals to m alpha t negative 2 alpha and m beta. Now you can see this 2 is the same dimension. We can just write m alpha plus beta t negative 2 alpha. So you can see this, the here is left hand side, right? They have a dimension of t which power of 1, and another part is this right hand side. So from dimension analysis, we know that these two sides must have a same this dimension, right? Now left hand side you can see only have the dimension over time. That means this the alpha plus beta must equals to 0, right? Because when alpha plus beta equals to 0, this m will power to the 0, that means equals to 1. So the dimension no longer exists, it just equals to the 1. Now t multiplied with the 1, right? You just get back t, which is what we want in this case. So we get the alpha equals to minus beta, right? This is just a simple mathematics. you negative both side with the beta. This you get the alpha equals to the negative beta. Now you can see here these two sides have a dimension of 10, and you can see here is a power of a 1, so 1 will equals to negative 2 is alpha. That means you divide by 1 over 2 from both sides, you get alpha equals to negative 1 over 2, right? So from here you substitute back this thing, you will get is beta equals to negative alpha equals to minus 1 over 2, and you get this is a 1 over 2. So let's rewrite this. Beta equals to 1 over 2. We take these two results. These two is an important result. We substitute back inside to this equation here. We get t equals to c k minus 1 over 2, and this m 1 over 2, right? You just substitute this alpha and the beta inside for this value. Now we can write this is equals to c square root of m over the k. Now for your information, although this is not important for now, this c actually will, this proportionality constant is actually equals to 2 pi. You will see I think in SEM 3 will be covered out in the later video. So here we form a formula using the dimension analysis, this concept same dimension for both sides of the equation. We get this is a 2 pi square root m over k. Now here is the example. I hope this is helpful.